Let's now take a look at how queues work, which is the next ADT that we'll be taking a look at. A queue is a first in, first out abstract data structure. It's a first in, first out ADT. To compare this with stacks, stacks were last in, first out. Queues are first in, last out. Beg your pardon, first in, first out. Where queues are typically implemented using an array, just like stacks. Now, to show you how queues work, you have to keep in mind that in this diagram, the front of the queue is here and the rear of the queue is here. As a result, you'll expect items to add to the queue from the behind or the rear and remove from the queue from the front. Try imagining a supermarket queue. You'll have people joining the supermarket queue from the end, in other words, the rear, and you'll have people leaving the supermarket queue from the front, which makes sense because that's essentially how the first in, first out, or the first come, first serve basis of a queue can be established, isn't it? Now, in order to add items and remove items from a queue, we have two operations associated with the queue. That's onQueue and dequeue. OnQueue is used to add an item to the rear of the queue, and dequeue is used to remove an item from the front of the queue. And just to show you a quick animation to see this in action, I can add 5 from the rear of the queue. That's called onQueue. And we can remove a 10 from the front of the queue, and that's called dequeue. Queues are used in a variety of different places. Queues are used in printers to maintain print jobs in order. Queues are used in CPU scheduling for OS process management. Queues are used in call centers to handle incoming calls of customers. And also, queues are used in breadth-first search algorithms to explore graphs level by level. Let's start by understanding how you initialize an empty linear queue. What exactly a linear queue is not quite apparent to us right now, but you'll understand what it means to be linear soon when we look at the second type of queue called circular queue. So as far as the syllabus is concerned, you'll be learning about two different implementations of a queue. That's a linear and circular. Of course, circular queues are what we use in practice because, frankly, circular queues solve a problem that linear queues suffer from, and that's that locations that become dereferenced at the front are no longer accessible in a linear queue. But of course, that problem and a lot of other things we'll look at the end of this video. Right. Now, to initialize a linear queue, we have to start by initializing an array because a queue is implemented using an array. So we'll set a fixed size to our array. Let's say that we have 5 items in our array, and we'll declare an array that has 5 items, thereby getting the indices 1, 2, 3, 4, and 5. And this array will serve as the structure for our linear queue. Of course, similar to stacks, we'll have an index 0, which keeps track of the initial value of rear pointer. In other words, one value less than the lower bound. And again, to remind you, 1 is the lower bound of the array and 5 is the upper bound of the array. Now, in this queue, you're supposed to consider wherever the lower bound is as the front of the queue. And you're supposed to consider wherever the upper bound is as the rear of the queue. Never mistake this. The upper bound is where the rear of the queue is. The lower bound is where the front of the queue is. So as a result, you'll expect items to be added from the rear, added from the top, and you'll expect items to be removed from the bottom, right? This is where onQueue will happen from this direction, and dequeue will happen from this direction, from the bottom. Please keep this in mind because at the exam, they may invert these indices, which in case means that dequeue should instead happen from the top and onQueue should happen from the bottom. But don't let these directions mess your understanding of a queue. A rear is always next to the upper bound. The front is always next to the lower bound. That will hopefully help you keep consistent with the definition of a linear queue. Now, as similar to a stack where we set stack full to the number of items our queue has, queue full will be set to the same thing. queue full will be the maximum number of locations our queue has. So as a result, queue full, beg your pardon, will be set to 5. Rear pointer will be set to 0 to indicate, sorry, rear pointer will be set to 0 to indicate that there are no items in our queue at the moment. So you can imagine that rear pointer initially points to 0, which is 1 less than the lower bound. But what exactly does rear pointer point to, guys? Rear pointer's job is to point to the item at the rear of the stack, of the queue. So in this case, we don't have any items, which is why rear pointer is 0. But if we add any items, the item that is currently at the rear of the queue will be what rear pointer points to. And front pointer similarly will be pointing to the front of the queue. In other words, the index of the item at the front of the queue. But of course, right now, since there's no front to the queue either, we'll be setting front pointer to 1. Of course, we don't set rear pointer and front pointer both to the same value because we always expect the front to be 1 more than the rear. If in case this changes, then of course we'll be encountering a different situation or a different problem, but that will be solved when we look at circular queues. But keep in mind, we set front pointer to 1 as our initial value. So you can always imagine that front pointer is ready or already pointing to the next item to remove, right? Front pointer is ready to remove the next item. So front pointer is always kept 1, 2, 3, 4, 5. It's always kept 1 ahead of the rear pointer in normal circumstances. So the front point is always pointing to the next item to remove. That's an easier way to think about it. Whereas the rear pointer is pointing to the item that was essentially last added to the queue or was last on queue. In other words, the last to remove from the queue. But again, to avoid any confusion, the front point is always the item at the front of the queue and it points to the next item to remove. So you can imagine that front pointer is the man that's responsible for dequeuing, whereas the rear pointer points to the item at the rear of the queue or the item or position where the next item should be added. In other words, rear point is where on queue plays its role. So dequeue points to the item at the front or the next item to remove. So front point is always 1 ahead of the rear pointer, whereas on queue points to the next item or the next position where the item should go, right? Rear pointer points to the location where the next item should be going. Or in other words, in this case, you can imagine that it's where the current last item that was added to the queue was placed, right? So in this case, we are setting rear pointer to 0 because there isn't anything in the queue. As a result, rear pointer is 0. But the next time we add an item, rear pointer will be set to 1. And that 1 position would be where the last item added to the queue will be. And you can imagine that therefore, rear pointer keeps track of the location or the index of the rear of the queue or the last item added or on queued to the queue. Okay, again, don't confuse yourself. Hopefully, these definitions make sense to you. If you have any doubts, feel free to rewind and watch this last couple of definitions. But if there's any questions, do let me know. Of course, this completes the 4-step process of initializing an empty linear queue. Now, to on-queue an item into this queue, what exactly should we do? Let's forget about step number 1, just like our stack process, because step number 1 only becomes relevant when the queue is full. And let's follow through step number 2 and 3. Let's imagine our initialized state of the queue, where queue full is 5, rear pointer is 0, and front point is 1, which is the state of the queue once initialized. To add an item to the queue or to on-queue an item to the queue, we first increment the rear pointer. We increment the rear pointer, thereby rear pointer becomes 1. And then we add the item to that position in the rear point, at that position in the queue. As a result, whatever item that we want to add will go to queue rear pointer position. That's whatever the index that the rear point is currently set to, we set the new value at that index of the queue. So 26, in this case, the example item will be set to that position in the queue. And then we rinse and repeat. We keep adding items, incrementing the rear pointer and adding the item to that position in the queue. Let me keep doing this until our entire queue is full, guys. So as you'd expect, we can add a bunch of random items like 32, 45, 63, and maybe 72. And as a result of each of these on-queue operations, the rear pointer should have incremented one by one by one by one all the way until 5. But let's say someone tries to on-queue an item well beyond 5. Of course, that isn't possible because the queue is full. So how do we detect if the queue is full? Similar to how we detect how a stack is full, we can check if the rear pointer is equal to queue full. If they are equal, yes, the queue is full. So if rear pointer is 5 and queue full is also 5, if rear pointer is therefore equal to queue full, we know that the queue is full. So therefore, only if rear pointer is less than queue full do we keep adding items. Otherwise, we can display an error message indicating that the queue is full. That's where step number 1 is important. And that's why these 3 steps is the proper way to essentially on-queue an item to a linear queue. Now, the pseudocode for linear on-queue is very simple. We implement it as a procedure because it doesn't return any items. We take an item as a parameter. We check if the rear point is equal to queue full. If so, the queue is full. Otherwise, similar to a stack, we increment our rear pointer and we add the item to that position in the queue. Now let's ask ourselves, how would one dequeue an item from a linear queue? Let's add a bunch of items to our queue. Let's say that the items in our queue are currently 25, 36, and maybe 45. And let's imagine that queue full in this case is 5 because that's the total number of locations our queue has. Rear pointer is set to, in this case, it will be set to 3, right? Because that's the last item added to the queue. And front pointer will be set at 1 because right now that's the front of the queue. Keep in mind the front is always here and the rear is always here. Don't forget that. Now, to dequeue an item, what exactly should we do? Now, unlike a stack, we won't be removing the item that was added last, right? The item that is removed, right, will be the one that was added first because the queue works in the first in, first out basis, unlike a stack which works on the last in, first out basis. As a result, here, what you'd expect is 25 was added first, 36 was added second, and 45 was added third. Therefore, because of the first in, first out basis, the first item to add to the queue, which in this case is 25, should therefore be the first item to remove itself from the queue. Thereby, 25 should be the item to get removed next. Now, how exactly do we remove 25 from the queue? If you remember my conversation from earlier, the front pointer is the guy that's responsible for dequeuing. And the front pointer always is the index of the next item to remove from the queue. And as you can see, the front point is 1. 1 is where 25 is. And voila, 25 is exactly what we should now remove. Perfect sense. I hope all this makes perfect sense to you. So as a result, we'll be removing the item pointed to by this front pointer. And the way we remove it is, again, let's ignore step number 1 for now. We'll first return the item at queue front pointer, right? Here, whatever item is currently at front pointer position, we'll remove that. Or we'll return that, sorry. And then, unlike stacks where the top point is decremented, in queues, we'll be incrementing the front point because the next item remove is 36. We have to keep going upwards every time we remove. And we have to, similarly, we're supposed to keep going upwards every time we add. But keep in mind, since we have 2 different pointers, the 2 different jobs, it doesn't matter that both items or both pointers are going upwards because when we add, we increment our rear pointer. When we remove, we increment our front pointer. So there's no conflicting interests. Both pointers have a specific job. So right now, when front pointer gets incremented to 2, we now know that the next item to remove is 36. And of course, as a result of updating our front pointer, you can expect that this 25 gets dereferenced Thereby, this would now be a garbage value in memory, which is free to be overwritten the next time an item is pushed, or in this case, on-queued back to the queue. Right, so again, we can keep doing this. We can keep returning items and increment in the front pointer, right? And you'll realize that this keeps going. And of course, the way we realize that we have no more items to remove is when the front pointer is greater than queue full. If the front point is greater than queue full, then we know that the queue is empty. Otherwise, we can keep removing or dequeuing items until the entire queue is empty. Now, the pseudocode for linear dequeue is again pretty straightforward. You implement it as a function because you return the item to dequeue. You return the item that was dequeued. Of course, similar to a stack pop operation, you initialize a declare item and you set the initial value of the item to be -1, which is a null indicator. If the queue front point is greater than queue full, let me know that the queue is empty. Otherwise, if the item exists to remove, if there is something to remove, then we set the current front pointer's location of the queue to be where the item is stored, thereby attaining a copy of that item. And then we increment our front pointer by 1, and we return that item to the user. Right, that is the pseudocode for linear dequeue. Now, let's understand a problem with linear queues. Let's try to go through these operations of a queue, guys, and see what exactly happens to our queue, our linear queue, as a result of going through these operations. At the exam, you may get questions like this, where you're supposed to execute these function calls and procedure calls on this linear queue and see what the output is, and you might get the same operation for stacks as well, where they give you a bunch of operations to perform on a stack or queue. So therefore, please be ready to do these kinds of operations, because it's important that you know how to work with in situation or in situ on queue and dequeue operations, because they might just throw a bunch of function calls at you and you are supposed to depict what the final queue will look like. So this will be good practice to see how these kinds of problems work, and you might get problems like this at the exam as well. Now we start off with an empty queue, where queue full will be set to 5, rear pointer will be set to 0, and front pointer will be set to 1. The first operation is to call on queue 15. Why call? Because on queue is a procedure, and we are supposed to thereby add number 15 into the linear queue. So the way we add number 15 into the linear queue is by, of course, incrementing our rear pointer. Rear pointer will be set to 1. That's where the item should thereby go, and the item that will go there is 15. And we keep repeating this. Next step, on queue 26, rear pointer becomes 2, 26 goes to location number 2. Call on queue 83, rear pointer becomes 3, 83 goes to location 3 of the queue. And then we have 2 dequeue operations. Cool. 2 dequeue operations. We are supposed to then dequeue the items at the front of the queue, 15 and 26. So what exactly do? We increment our front pointer once after removing 15, and we increment our front pointer again after removing 26. So now you can imagine that rear pointer and front pointer are both at 3, which is pretty meaningful because the only item that is in our queue is 83. So just to clean things up, as a result of all these operations, you'll expect the front pointer and rear pointer to both be 3. Now let's call on queue again. Let's try and call 73. Let's try and call on queue 73, thereby adding one more item to our queue. Now, of course, the next item will be added to whatever the rear pointer plus 1's position will be. So rear pointer plus 1 will be 4. That's where the next item will go. So therefore, 73 will go to position number 4. And then we'll call on queue 45, the next operation, thereby incrementing rear pointer again and allowing us to add 45 to location number 5. But now, what happens to this operation? Call on queue 62. Now, rear pointer and queue full are both equal, which is the condition under which we know that our linear queue is full. But honestly, if you think about it, do we not have space at the front where this 62 would have possibly added? couldn't the 62 have gone to the front, guys? I mean, it could have. But the way that the linear queue works, it works in this rear to front fashion from top to bottom or bottom to top. It is not able to reuse locations at the front because it's linear. That's what linear means. It's only able to work on a single dimension from left to right or top to bottom. As a result, even though we do have free locations in the front, those free locations are unusable because of how a linear queue works. And that, ladies and gentlemen, is the problem with linear queues. So in three simple phrases, when the front pointer reaches queue full and there is space remaining at the front of the queue, these spaces becomes unreachable. And that's what linear queues suffer from. Now, to solve this problem, we can use a circular queue. A circular queue is a similar first in, first out data structure, but the idea is that items from the front can circle back to the rear or vice versa. The items at the rear can circle back to the front. The last position of the queue is thereby connected back to the first to form a circle. And similarly, circular queues are implemented using arrays. Now, the pseudocode for linear on queue is what you see here. And I'm going to show you how this changes to make do for circular on queue. Look at this very carefully, guys. Look at the animation and see what changes occur from when we go from the pseudocode for linear on queue to circular on queue. See what happened. Feel free to rewind back and see what exactly the changes are, because you should hopefully see what changes happen. It's not a lot of changes, just a minor number of changes, right? When you do circular on queue, guys, when rear pointer equals queue full, you don't declare that the queue is full. The queue is only full when this new variable called queue length, which increments each time an item is added and starts at 0, is set equal to queue full. Only when queue length is equal to queue full do we know that the queue is full. But if queue length is equal to queue full, if queue length is not equal to queue full, that means there is still space remaining in the queue, but for some reason the rear point is equal to queue full, what that indicates logically is that there is space at the front, right? But that space is currently inaccessible to us. So in order for us to access the space at the front, we can reset our rear pointer back to 1, which is what that circular operation actually means. It means to set the rear pointer back to the beginning. But otherwise, if there is space, if queue length is less than queue full, but the rear point is also not equal to queue full, if rear point is less than queue full, then we can keep incrementing rear pointer by 1, allowing us to add the rear pointers, add the item to that position, to the rear pointer position of the queue, and thereby increment queue length by 1. And then again, to take a look at what changes we do to circular Dequeue. Beg your pardon, guys, this slide seems to have a small error. This is the linear Dequeue operation. This is the linear Dequeue operation, which is what we learned a while ago. Let's see what changes happen to this operation to make do for the circular Dequeue operation. So in order to make do for the circular Dequeue operation, we use our queue length variable to check if our queue is full, beg your pardon, to check if our queue is empty. If the queue is empty, of course, we know that the queue is empty and we output a message. But if the queue length is not equal to 0, that means there is space left in the queue, but preferably in the front or the rear, which we don't know. But to detect that, we can check if our front point is greater than queue full. If so, if front point has exceeded queue full, then we know for sure, okay, the space must exist back at the front. So we can reset front pointer back to 1. Otherwise, we can set front pointer to front pointer plus 1 and set our queue length to queue length plus 1. As usual, we are supposed to set item to queue front pointer to save the item to return before we update our front pointer. And if nothing gets returned, then we can set our item to null as well. This, ladies and gentlemen, completes a lesson on queues covering both linear and circular queues.